Why this feels hard to read? You feel like you get the idea but not deeply because it mixes multiple layers at once. NIC to driver to IP to UDP. It uses formal academic language. It describes the entire receive path in one long paragraph and it assumes you already understand the hardware or software division in NIC filtering. So don't worry, this is normal. Let's rewrite it in plain engineering language. What this whole section is really saying, when a multicast packet arrives at your laptop, first, the Ethernet NIC hardware decides, should I even pass this frame up to the OS? Second, if yes, the driver and OS decide, is this packet really meant for any process on this computer? Third, if yes, UDP or TCP decides, is any application listening on this port? Only if all of these say yes, does a packet finally reach your application. Instead of broadcast everyone receives anything, multicast tries to stop hosts that don't care from wasting CPU. Why do we need multicast tables? Because your NIC can't magically know which multicast groups your OS is interested in. Example, your app joins group 239.255.255.250 or MDNS or multicast DNS 224.0.0.251 FF02 FB. Your NIC needs to be told only forward Ethernet frames whose destination MAC matches the multicast MAC from these groups. Otherwise, it would have to pass all multicast traffic to the OS. The OS would waste time filtering packets it doesn't need. So NICs keep a list or hash table of multicast MAC address that the OS has joined. Two kinds of NIC designs. This confused you. First, NIC with the multicast address table, like a whitelist. Keep up to n multicast MACs, only pass frames matching them. Second, NIC with hash filtering. Memory is smaller, so hash MAC to bit vector index. If bit equals to 1, then accept. This can produce false positives. Accept multicast frames we didn't ask for, but no false negatives. Never drops a frame we should get. Meaning, if the NIC is unsure, it forwards the packet upward. The OS will finish filtering in software. This is the key idea. NIC filters as much as it can. OS filters the rest. The complete receive path. Let's rewrite the book's whole flow in a clean ladder. Step 0. Frame arrives at NIC. NIC checks CRC not corrupted. VLAN tags match. Is destination MAC unicast to this machine? Broadcast. Multicast in multicast table or hash? If no, NIC drops it. If yes, pass to device driver. Step 1. Device driver filters again. The driver now checks, is this Ethernet type supported? IPv4, IPv6, ARP, etc. If not supported, drop. If supported, pass to IP layer. Step 2. IP layer filters again. IP checks destination IP address. Does this host belong to that multicast group? Did OS joins the group on this interface? If not, drop. If yes, pass upward. Step 3. UDP or TCP filters again. UDP checks, is any application listening on this port? If no, discard and reply with ICMP port unreachable. If yes, deliver to application. Why this was invented at all? The final paragraph explains the motivation. Broadcast makes every host waste CPU processing packets not meant for them. So that's the reason why you need to filter, because multicast is broadcast that the MAC subscribe to. Imagine 50 hosts In a LAN, only 20 are interested in a video feed. If broadcast, all 50 must receive and process every packet unnecessarily. If multicast, only the 20 hosts who join the group get it, so multicast reduces system load. How this connects to your earlier questions? Multicast IP map to multicast MAC. NIC checks MAC first. OS checks IP group membership second. UDP or TCP check port last. That is NIC to driver to IP to UDP to your application. The NIC filtering exists because one multicast MAC address can represent multiple IPv4 or IPv6 multicast addressing. Mapping is not one-to-one. Many NICs can store unlimited entries. So the table is limited. That's why sometimes you need to have that vector type. Some NICs use hashing, which means false positive. Therefore, OS needs a second filtering stage. This matches what you asked for earlier. Why do I need netsh show joins or netstat-gn? Because the NIC only understand MAC addresses, but application join IP multicast groups. So netsh or netstat show which IP layer multicast groups the OS has joined, not what the NIC knows. Super short summary. Switch sends multicast frames to all ports in VLAN. So the switch are responsible for sending that. They copy the datagram to all the switch, and then NIC tries to reject unwanted multicast frames. If NIC passes them, OS filters again at IP. If IP accepts, UDP filters again by port. Only then does your app receives the packet. Multicast is broadcast but smarter. Why you can understand the concept but not feel it deep? Because this topic mixes hardware architecture, Ethernet design, IP multicast addressing, NIC driver implementation, OS network stack, application socket API. You already understand the idea. Filter at multiple levels. You just didn't yet build a clean mental picture of the whole flow at once. Now you have that picture. Yes, the NIC has memory. A NIC network interface card is not just a wire, it's a small computer with a processor, microcontroller, or ASIC logic, its own RAM, often a few KB to a few MB, registers, DMA engines, firmware. That memory stores things like MAC address tables, unicast plus multicast, configuration registers, buffers for RX/TX frames, hash filters. So yes, when the OS joins a multicast group, the NIC stores that information in hardware memory. How multicast filters look in real hardware? A. Table-based NIC whitelist. Many NICs support something like this. Multicast filter table. Inside it, number 0 equals 01 colon 00 colon 5 E colon D0. And then for number 1 equals 01 colon 00 colon 5 E colon 00. And then etc. And then number 2 until you get it. This is literally an array in NIC RAM. Some NIC support 32 entries, some support 128, some support 512. When an Ethernet frame arrives, here's the if-else code. If destination underscore MAC in multicast filter table, colon, then accept, else, colon, drop before the OS ever sees it. This saves CPU time. B. Hash filter NIC less memory. Some NICs don't have space to store many MAC addresses, so instead they support something like 64-bit mask bitmap. Example, hash table bits equal 0B001000100, etc. The NIC uses a hardware hashing function like this: index equal hash argument MAC underscore address percentage 64. Comment, this gives number 0 to 63. Then we have a code: if hash table bits argument index equal 1, accept, else reject. This is very fast in hardware. So this is how you configure that vector type or small memory NIC. Why memory is smaller? Because storing 128 MAC addresses needs space. A hash bit map, 64 bits or 256 bits equal tiny. So hash filters are less accurate, much cheaper in hardware. Trade-off: method, full table; memory, higher; accuracy, perfect. Method, hash; memory, very small; accuracy may accept unwanted frames. If unwanted frames come through, the OS traps them later. Why the NIC remembers MAC not IP? Because NIC operates at layer 2. NIC never parses IP headers. NIC only sees Ethernet header, destination MAC, source MAC. IP addresses exist in IP header, but the NIC does not code IP in hardware. Too expensive, too slow. Therefore, the OS decides which IP multicast group to join. The NIC only stores the MAC version of those group. Why one multicast MAC can represent many IPs? Because of the mapping rules. IPv4 mapping, simplified, take IPv4 multicast 224.0.0.251, convert last 23 bits into MAC, like this: 01:00:5b::xx::xx::xx. This means 2 raised to 23 8 million IP multicast addresses map into 2 raised to 23 MAC values only in the lower 23 bits. So different IP multicast addresses can produce the same MAC address. That is why NIC must filter only on MAC. OS must do a second filtering stage based on IP. 6. Switch behavior. Does it copy frames? Yes. If a switch does not have IGMP snooping enabled, multicast is treated like broadcast, like copy the data sent to every port in VLAN. So the IGMP snooping enabled on switch is what actually allow the multicast. If IGMP snooping is enabled, switch listens to IGMP joins, switch learns which ports want the multicast, switch forwards only to ports with subscribers. This is why multicast scales. How this connect to real computer hardware? Now we go deeper down to what you ask: how this connect to machine language, binary encoding, and real hardware execution. The NIC is really just a state machine. At its lowest level, the NIC does not run C++ code. It is implemented in gates, multiplexers, and microcode. When a frame arrives, first, bits are serially clocked into shift register. Second, hardware compares destination MAC against hash engine circuits, COM/TCOM memory, content addressable memory if using a table. Third, comparator outputs true or false as logic signal. Fourth, if true, DMA push frame into RAM buffer. Fifth, NIC interrupts the CPU. This is just electronics. Example machine level. Imagine this simplified logic circuit. Incoming underscore MAC XOR stored underscore MAC equal 6 zeros. Then match equal 1. Or for hash, bits equal hash function argument MAC or parameter MAC. If bit table bits argument bits equal to 1, accept, accept. This is not software. It is literally flip-flops, combination logic, address decoders, memory cells. Where are the hash bits stored? Inside NIC SRAM, something like hash bit map: 0100. So it's a 32-bit. This is just 32 or 64 bits of hardware memory. Where is the code? NIC firmware and drivers implement the higher level logic. For example, NIC driver code simplified C like void NIC underscore join underscore multicast argument MAC underscore address underscore MAC. Inside that, next line, hash equal hash underscore function, argument MAC percentage 64 semicolon, next line NIC 2 hash underscore table argument hash equal to 1, then closing semi curly bracket. NIC hardware logic, combinational logic matrix if argument hash table argument hash argument MAC equal to 1, next line pass underscore frame open and close parenthesis semicolon, next line else, next line drop underscore frame open and close semi-curly bracket. This is how the code becomes logic. How this relate to DLW-1 book and CPU data flow? You ask, how this connect to a binary encoding, arithmetic instructions, memory access instruction, etc. Connection, the NIC firmware instruction, if any, are machine code just like CPU instructions. But packet acceptance is usually not firmware. It is hardwired digital logic. The NIC only wakes the CPU when it has a relevant frame. So, layer, Ethernet MAC filter, who makes decision, NIC hardware logic. Layer, IP filtering, who makes decision, OS kernel logic. Layer, UDP port filtering, who makes decision, OS plus socket buffers. Layer, application processing, who makes decision, your program. So NIC filtering exists because reading every multicast frame wastes CPU. Where we are in the network receive path, when a UDP multicast datagram arrives, the filtering path is NIC hardware to device driver kernel to IP layer kernel to UDP layer kernel to socket buffers kernel memory to user program reads it. We already covered NIC filtering. Now we are at OS plus socket buffers. This is the layer where UDP port filtering and QUIC fit in. First, what are socket buffers? A socket buffer is simply memory inside the kernel where incoming or outgoing data is temporarily stored. So this is how kernel allocate temporary memory to that process to be able to connect to the internet. Each open socket has one or two buffers. Direction, receiving, name, rec vbuff, argument so underscore rcv buff, sending, name, send buff, argument so underscore snd buff. They are in kernel memory, not visible directly to user programs, FIFO queues. So when UDP receives a packet address to a particular port, it places the data in that socket's receive buffer. And if no process has the UDP port open, the packet is dropped and OS may send ICMP port unreachable. So this mapping is what allows you to be able, the OS actually provide port numbers in each process and put that in this socket, and it has an algorithm to be able to choose how it will provide that port number, and it's efficient. That's why you're able to maintain different connection or open different tab in your browser. UDP port filtering. UDP has no connection state. So the rule is simple. If destination UDP port belongs to an open socket, deliver to that socket buffer, else drop packet. Example, if UDP underscore rec v from function is waiting on port 5353 MDNS, then incoming frame to NIC to OS to UDP to port 5353 socket buffer, your app later calls rec v from argument sock comma buffer comma size and pulls the data out of the receive buffer. Third, how this connects to QUIC. QUIC is built on top of UDP, so UDP doesn't provide retransmission, congestion control, handshake, streams. Everything above it is QUIC's job. How QUIC fits NIC to kernel UDP to UDP socket buffer to QUIC stack. So QUIC reads raw UDP datagram from the socket buffer, implements reliability, flow control, AUX, encryption, etc. QUIC is basically TCP rewritten in user space, running over UDP. QUIC does not bypass socket buffers. QUIC still use the same UDP socket receive buffer that any UDP program uses, only the payload format is QUIC frames. So it still uses UDP. How this connects to multicast? Multicast UDP delivery path. Switch forwards, then NIC accept, then kernel UDP stock, then port filter, then socket buffer, then up. If your program did not join the multicast group, NIC or OS drops the traffic. If your program did join, NIC tries to filter in hardware, MAC level, OS filters again by the destination IP multicast group, UDP filters again by destination port. Finally, data ends up in your socket buffer. Why socket buffers exist? Two problems exist without them. A. CPU and application timing mismatch. Network packets sometimes arrive faster than the user programs can run. Buffers allow NIC and OS to work fast and continuously. User program to read whenever ready. B. Protection. Applications cannot access kernel memory directly. Socket buffers prevent corruption and for security, allow multiple sockets to coexist. 6. What happens if socket buffers fills up? UDP behavior. If buffer is full, drop new datagram, no retransmission. Because UDP is best effort, QUIC notices drop and retransmit because QUIC has its own reliability logic implemented in user space. This is one reason QUIC performance is often smoother than TCP. It can tune transmission behavior for real-world condition. 7. Where socket buffers live? They exist in the kernel, normally in Linux, struct, sock, and sk_buff, skb, Windows, afd.sys buffers, BSD or Mac OS, mbuff. Example for Linux, incoming frame, NIC DMA writes packet to kernel memory, driver wraps it in an sk_buff, protocol handler pushes into socket, rec vq, program reads the queue later. Bringing all layers together, here's the full pipeline with everything. Ethernet frames arrive, NIC hardware, CRC check, destination MAC filter, hash table or direct table checks. If accepted, kernel driver place into packet buffer, sk_buff, identify protocol via ether type. Then in IP layer, check destination IP, check routing and group membership. Then in UDP layer, check destination port. If no socket bound, plus drop and maybe send ICMP. If socket bound, to deliver to its socket buffer. Application reads from socket buffer if QUIC, parses QUIC frames, handles streams, ACKs, retransmission, encryption, etc. Why all these filters exist? Because without filtering, every packet would wake the CPU, every packet would run through IP, UDP, QUIC, user code, even if no program wants it. Filtering saves CPU cycles, memory, power. At each layer, more precise checks occur. Summary, concept, socket buffer, meaning per packet kernel memory queue for incoming or outgoing packets. UDP filtering, meaning drop packets not matching an open port. QUIC runs on top of UDP and reads from the same socket buffers. Relation to multicast. Multicast packets delivered only if NIC, OS, and UDP socket all accept. Why needed? Prevent CPU being overloaded by traffic not meant for your process. Now, an application watching a 2-hour YouTube video does not send only one UDP datagram. It sends thousands to millions of UDP datagrams. The text we quoted how UDP write calls to map network packets, not that the only one packet is used per session. So each UDP write, of course, has its own datagram, unlike with TCP. So that's the intro of our next topic. So it's not unlike TCP that it can choose the sequence and the slice of each byte. UDP actually have one datagram in each write, and it actually have thousands to millions of UDP datagram per session. common for a long YouTube video. So what the sentence really means. UDP behavior: when an application writes data to a UDP socket, like send to or write, one write equal one UDP datagram equal one IP packet. The OS does not split it, combine it, or reorder it. If you send 1 kilobytes, 1 UDP packet. If you send 10 kilobytes in one write, still 1 UDP packet, and it may be dropped if too big. And we will also discover that these are being handled by browser nowadays. But if you have an app that relies in UDP that actually needs to configure up to this layer, therefore you need to implement this, because this is one of its rules. So application write number 1 equal UDP datagram number 1, application write number 2 UDP datagram number 2. So each read and write consists of what do you call that? Yeah, consists of UDP or its corresponding datagram. UDP is message oriented. TCP behavior contrast. TCP is stream oriented, meaning the application may write 100 bytes 10 times. The OS or network stack might send this as 1 packet, 3 packets, 10 packets. It decides based on congestion, Nagel's algorithm, window sizes, etc. So app writes A, B, code, C. TCP might send 1 packet containing ABC, or app writes 1 MB. TCP might fragment into many packets. So the difference aspect relationship between application write function and packet sent. UDP 1 write equal 1 packet. TCP no fixed relationship. Aspect fragmentation. UDP not automatically change. Packet may be dropped if too large. TCP automatically split or combine. Aspect orientation. UDP message oriented. TCP stream oriented. Now your main question: if I stream a 2-hour YouTube video, does UDP sends only one datagram? No. Even if YouTube were using UDP, older devices sometimes use QUIC over UDP, many use TCP. It would still send a new UDP datagram for each chunk of data, thousands or millions of them. Example scale: 2-hour documentary, maybe 3 gig of data. Typical UDP datagram payload is less than 1/200 bytes. So this is the key. Each write should be less than 1/200 bytes, because that's implemented in the UDP protocol, which we will discuss further in the next video in PMTU. Number of datagrams needed. So we have here 3 billion bytes over 1/200 equal 2.5 million datagrams. So millions of writes, 2 millions of packets. So if you have millions of writes, it also have millions of datagrams and packets. UDP never sends 1 packet for the whole session. Why the system or sentence seems confusing? The book was not talking about video streaming scale. It was only explaining the packet mapping rule. UDP does not break or coalesce writes. TCP does. Simple analogy: think of sending letters. UDP, every time you write a message and put an envelope in the mailbox, the post office sends exactly that envelope. TCP, you write many notes and drop them in a bin. The system may put multiple notes into a single envelope or split one note across multiple envelopes. Final summary: does UDP send just 1 packet for a session or video? No. Every write function usually becomes 1 packet, so streaming involves huge numbers of datagrams. What does the sentence mean? UDP: 1 application write to 1 packet. TCP applications do not directly correspond to packets. User datagram protocol and IP fragmentation. UDP is a simple datagram-oriented transport layer protocol that preserves message boundaries. It does not provide error correction, sequencing, duplicate elimination, flow control, or congestion control. It can provide error detection and includes the first true end-to-end checksum at the transport layer that we have encountered. This protocol provides minimal functionality itself, so applications using it have a great deal of control over how packets are sent and processed. Introduction: applications wishing to ensure that their data is reliably delivered or sequenced must implement these protections themselves. Generally, each UDP output operation requested by an application produces exactly one UDP datagram, which causes one IP datagram to be sent. This is in contrast to a stream-oriented protocol such as TCP, see Chapter 15, where the amount of data written by an application may have little relationship to what actually gets in a single IP datagram or what is consumed at the receiver. In addition, there is no protocol mechanism to prevent high-rate UDP traffic from negatively impacting other network users. Given this lack of reliability and protection, we might be tempted to conclude that there are no benefits to using UDP at all. This is not true. However, because its connectionless character, it has less overhead than other transport protocols. In addition, broadcast and multicast operations, see Chapter 9, are much more straightforward using connectionless such as UDP. Finally, the ability of an application to choose its own unit of retransmission can be important consideration. Figure 10.1 shows that encapsulation of a UDP datagram as a single IPv4 datagram. The IPv4 protocol fields has the value 17 to indicate UDP. IPv6 uses the same value in the next header field. Later in this chapter, we will examine what happens when the size of the UDP datagram exceeds the MTU size and the datagram must be fragmented into more than one IP layer packet. So we kind of discussed that in the fragmentation in the IP part, but and also we discussed that it's really happened because of most app nowadays actually implements the minimum 1200 bytes size. Now figure 10.1, encapsulation of a UDP datagram in a single IPv4 datagram, the typical case with no IPv4 options. The IPv6 encapsulation is similar. The UDP header follows the header chain. UDP header. Figure 10.2 shows a UDP datagram including the payload and UDP header, which is always 8 bytes in size. Figure 10.2, the UDP header and payload data area, the checksum field is end-to-end and is computed over UDP pseudo-header, which includes the source and destination IP address fields from the IP header. Thus, any modification to those fields, i.e. by NAT, requires a modification to the UDP checksum. So this is why it provides its end-to-end reliability or security because of this checksum inherently built on its structure. Port numbers act as mailboxes and help protocol implementation identify the sending and receiving processes. They are purely abstract. They do not correspond to any physical entity on a host. We will also discuss that the port actually changes over time. And once you close the process, that port will become available for other process. In UDP, port numbers are positive 16-bit numbers, and the source port number is optional. So it's actually optional, but most hosts actually implement this to identify itself. It may be set to 0 if the sender of the datagram never requires a reply. Transport protocols such as TCP, UDP, and SCTP use the destination port number to help demultiplex incoming data from IP. So that destination port number are actually required for for SCTP, UDP, TCP in case you want to receive it. So the port number can't be 0, the source port number can't be 0 if you want to demultiplex it or to receive that packet from that recipient. Because IP demultiplexes the incoming IP datagram to a particular transport protocol based on the value of the protocol field in the IPv4 header or next header field in the IPv6 header, this means that the port numbers can be made independent among the transport protocols. That is, TCP port numbers are used only by TCP and UDP port numbers only by UDP, and so on. A straightforward consequence of this separation is that two completely distinct servers can use the same port number and IP address, as long as they use different transport protocols. Note, despite this independence, if a well-known service is provided or can conceivably be provided by both TCP and UDP, the port number is normally allocated to be the same for both transport protocols. This is purely for convenience and is not required by the protocols. See iPort for details on how port numbers are formally assigned. Referring to figure 10.2, the UDP length field is the length of the UDP header and the UDP data in bytes. The minimum value for this field is 8 except when UDP is used with IPv6 jumbograms. See section 10.5. Sending a UDP datagram with 0 bytes of data is acceptable, although rare. Note that UDP length field is redundant. The IPv4 header contains the datagram's total length. See chapter 5. And the IPv6 header contains the payload length. The length of UDP or IPv4 datagram is then the total length of the IPv4 datagram minus the length of the IPv4 header. A UDP or IPv6 datagram's length is the value of the payload length field contains in the IPv6 header minus the length of any extension header unless jumbograms are being used. So you can actually calculate it by just having the total length of the IPv4 datagram minus the length of the IPv4 header. So that's the length of the entire UDP, because again you start from IP then goes to the transport layer. A UDP or IPv6 datagram length is the value of payload length. So per IPv6, it's the payload length contained in the IPv6 header minus the length of any extension header unless jumbograms are being used. So again, it also deducted the header. So that's kind of the formula. It's payload length, or the, in case of IPv4, the total length minus the header length. In either case, the UDP length field should match the length computed from the IP layer information. So that length in UDP is kind of redundant, but that's just the way it is. Why is your browser using high port numbers like 49125 plus instead of the first range? The first range of port 0 to 1023 is reserved for a well-known ports. So this is where you get the TCP, DNS, SSH, etc. Those are well-known ports assigned by IANA for well-known services. But for example, you want to open session with Chrome, you would need to have or use this high range ports. So like this port range 0 to 1023, name well-known ports. Examples: 80 equal HTTP, 443 equal HTTPS, 53 equal DNS. Regular applications are not allowed to randomly use this, because doing so could conflict with system services. Browsers don't need a fixed port. When your browsers connect to a web server, it connects to port 443 on the server HTTPS. Uses a temporary port, ephemeral or random, on your machine on its high ranges. So it is in combination of that well-known ports that is the confusion. So ephemeral ports 4915.265.535 is in use in combination to specify or distinguish each process on the socket buffer. Now Windows and most OSs use 4915.265.535 For temporary outbound connections, so your browser is not hosting a service, it is initiating a connection. So the OS picks a temporary port in the high range. This is expected, normal, and correct. Second, but I thought TCP and UDP are assigned in the first range. Misunderstanding. The service ports like TCP 80, UDP 53 live in the low range. The protocols TCP and UDP themselves are not limited to any port range. TCP and UDP can use any port number. The ranges apply to applications, not the protocols. Why do you still many why do you still see many TCP connections if QUIC uses UDP? Because the internet is in a transition period. QUIC HTTP/3 uses UDP. Modern browsers try first HTTP/3 QUIC over UDP. Second, if the server doesn't support it, fall back to HTTPS, HTTP/2 or HTTP/1.1 over TCP. Most websites still support both. So on a real machine, Chrome may use UDP for some sites, TCP for many others. Your system services and apps use TCP too. Windows processes like svc host.exe, lasss.exe, spoolsv.exe, Viber, Spotify, Chrome internal processes have many internal TCP connections, so it's normal to see a lot of TCP even in 2025. What your NetStat output is showing, let's decode it simply. So for my laptop, a local system services listening on low ports, example, TCP 0.0.0.135 listening to svc host.exe, TCP 0.0.0.445 listening. These are Windows services running servers locally. 135 is equals to RPC, so that's for the first TCP. 445 is equal SMB file sharing. Now 623.16992 equal Intel AMT services. These are not connections going out, just listening sockets. Tons of browsers outbound connections. Examples: TCP 192.168.1.47:54319, 172.64.148.235:443. Establish Chrome.exe. This means Chrome use local ephemeral port 5319. Connecting to port 443 on a server, TCP is used for HTTPS. This is normal web browsing traffic. See 127.0.0.1 connections. Example: TCP 127.0.0.1:49795, 127.0.0.1:49796. Establish Viber.exe. This means two processes on your computer are talking to each other through the loopback interface localhost. So these are the loopback that we have discussed in the previous video that has not been used for multicast. Now it's being used inside the machine. No internet involved. UDP entries, example, UDP 0.0.0:5353 **Chrome.exe. This is UDP port 5353 equal MDNS, multicast DNS. It's used for device or service discovery on the LAN. So this is actually how you discover devices, kind of like an ARP within your LAN. So this is how you use also to find the router's MAC. Now many apps like Chrome, Spotify, etc. also use this. Summary, putting everything together. Concept: TCP and UDP are transport protocols, meaning they are not tied to any single port range. 0 to 1023 ports, reserved for well-known services, DNS, HTTPS, SMB, etc. 49152 to 65535 ports, ephemeral ports for outgoing connections. Browsers use high ports, meaning because they are clients, not servers. So that's also the distinction. For browsers, like for any client, you use those ephemeral ports, but for servers, of course, you use those well-known ports. You will see TCP because not all services or websites use quick yet real-world analogy. Calling someone on the phone, the website's port 443 is like destination of phone number. Your local random port like 54321 is like temporary line your phone uses to make the call. Multiple tabs equal multiple phone calls, each using a ephemeral number. Why is the ephemeral port range 49152265535? Ephemeral ports are temporary ports used by clients when they initiate outbound connections, like your browser or Spotify connecting to a server. Who decides the range? IANA or IANA recommends 0 to 1023 well-known system ports, 1024 to 49151 registered ports, 49152 to 65535 ephemeral or dynamic ports. Operating systems adopt these for consistency. How does the OS implement ephemeral ports? An OS kernel has a port allocator in its TCP or IP stack. When a client program calls connect function and does not specify a local port, the kernel first checks the configured ephemeral range. Second, scans for a free port. Third, binds the socket to it. Fourth, returns that assigned port to the application. Windows implementation, you can inspect the current range with netsh int IPv4 show dynamic port TCP or netsh int IPv6 show dynamic port TCP. You can change the range netsh int IPv4 set dynamic port TCP start equal 50k or 50,000 num equal 10,000. Internally, the logic is in the Windows TCP or IP stack, not user mode code. It's basically for port in ephemeral underscore range, if port unused, assign and break. Linux implementation, check current range, cat /proc/sys/net /ipv4/ip underscore local underscore port underscore range. Then set a new range, echo, code 3000 or 30,000 space 45,000 /proc/sys/net/ipv4/ip underscore local underscore port underscore range. Again, kernel code does the same thing. Search for a free port in the configured low-high range. So the kernel, not IANA, enforces the range. IANA only defines the convention. Third, difference between a process and a service. Feature, what is it? Process, a running instance of a program. Service, a background process with a defined life cycle managed by the OS. So it's kind of like a daemon application that has its start and end cycle. When does it run? Process, only when launched by a user or app. Service can start at boot and run without login. Who controls it? Process, the program itself. Service, Windows Service Control Manager, SCM. Systemd for Linux, Launchd, etc. So the services are controlled by the OS, while the process are controlled by the program or the code you've written. Example, a process is a Spotify.exe, a service is event log, SVC, host.exe, DNS client. All services are processes, but not all processes are services. A service is basically process plus metadata plus manage startup / stop rules. So every process is a service. All services are process, but not all process are services. How to tell what each PID is doing? Windows, you already use the right commands. Process to PID, task list /fi, code PID space EQ space 10436, or get -process -id 10436. Service owning a PID, task list /svc /fi, code PID EQ4. This is how you figure out that many ports are owned by svc host.exe because it hosts multiple Windows services. See which executable own support. 2 best tools, CLI, netstat space dash abno. It shows local address, remote address, port, state, PID executable. For GUI, you can see that in TCP view, sysinternals. Fifth observation, TCP 192.168.1.47:54531 to server 443 establish, then PID 6148 Spotify.exe. You can conclude Spotify opened many short-lived TCP sessions. Each uses a different ephemeral client port in the 49XXX to 54XXX range. Browsers processes like Chrome or Edge behave the same way. Lots of concurrent outbound sessions. Listening 445/PID4. PID4 equals system kernel process, not a normal executable. Ports like 445 SMB 135 RPC are low-level system network functions. 6. Why so many time_wait ports in your laptop or in my laptop? After a TCP connection closes, the client socket enters time_wait, typically 2 times MSL equal to 40 seconds on Windows to ensure late packets don't get reused in future connection. This is normal for busy clients like Chrome or Spotify. Final quick summary, ephemeral ports chosen dynamically by kernel TCP stack. Default YANA recommended range 49.152.265.535. OS allocates next free port when an app calls connect function. Process versus service. Process equal running program. Service equal process managed by OS with controlled startup or shutdown. Mapping PID to activity. Task list /fi get process by PID. Task list /svc see which services a PID host. Netstat -abno /tcp view show port to PID to executable. Your output shows Spotify, Chrome, Viber, etc. opening many client sockets. Windows system services listening on well-known internal ports. Lots of time_wait from closed client sessions, which is normal.